Bismillahirrahmanirrahim. In today's video, we will discuss about how to improve steady state error via cascade compensation. In this figure, the gain K is shown and the plant is GFS. There are three poles. So because this is in the root locus, so angle criterion is followed or multiple of 180. If we simply adjust the gain, the steady state error will not be reduced. The reason is because the system type is type 0 system. We have no integrator in this system. Steady state error will be present. Although transient response is satisfactory, we do not want to change the transient response. The only changing required is in the steady state because we will have steady state error. And how much the quantity of steady state error will show in the next slide. We want to reduce the steady state error without affecting the transient response. Let's suppose we have step input. Type 0 system. For type 0 system, we want to enter in this value. We will have finite steady state error. For ramp input, we will have infinite error, and for parabola input, we will also have infinite error. So we want to reduce this error. We need integrator. Integrator will reduce the steady state error, but in the same time, we also want that no change in the transient response. So how this will be accomplished? We have introduced a integrator in the forward path. This is our compensator. Because S is on the origin, so there will be pole on the origin. Now the root locus has been changed. Also, the angle criterion is not followed. The sum of angle is not equal to 180 odd multiple. Previously, this was the root locus. Now the root locus has been changed, and this is our new root locus with compensator. This technique is called the ideal integral compensation, which uses a pure integration to replace an open loop forward path pole at the origin, thus increasing the system type and reducing the error to zero. The second technique does not use pure integration. This compensation technique places the pole near the origin, and although it does not drive the steady state error to zero, it does yield a measurable reduction in the steady state error. While the first technique reduces the steady state error to zero, the compensator must be implemented with active networks such as amplifier. The second technique, this one, although it does not reduce the steady state error to zero, does have the advantage that it can be implemented with a less expensive passive network that does not require additional power sources. A compensator with a pole at origin and zero close to the pole is called ideal integral compensator, like this. The next technique, the next controller is the PI controller. PI controller uses both proportional and integral controller. This is the gain of proportional and this is the gain of integral controller. So P and I are connected in parallel. The error and the integral of error are fed forward to the plant. The gain of proportional is changed to vary the transient response. If we want to achieve faster transient response, we will increase the value of this proportional gain. And if we want to reduce the steady state error, we will change the value of integral compensation. Integral here. The system has both proportional and integral control. The alternate name, therefore, is PI controller, and it is widely used in different applications of the control systems. Ideal compensators are implemented with active networks, require amplifier and additional power sources. The next one is lag compensation. Ideal integral compensation with its pole on origin requires an active integrator. If we use passive network, the pole and zero are moved to the left close to origin as shown in this figure. See, one may guess that this placement of the pole, although it does not increase the system type, does yield an improvement in the static error constant over an uncompensated system. The A is uncompensated system. In B figure, we have used compensator. This is a pole zero plot of the compensator. We can see from this static error constant for the uncompensated system, this is static error constant, while for the compensated system, the static error constant will be increased. So overall, the steady state error will be reduced for the lag compensation. So what will be the effect on transient response? In this figure, the effect on root locus of adding the lag compensation is shown. The uncompensated system in the figure A, the root locus is shown where point P is assumed to be the dominant pole. If the lag compensator pole and zero are close together, the angular distribution of the compensator to point P is approximately 0 degree. Thus, in this figure B, where the compensator has been added, point P is still approximately the same location on the compensated root locus. So, what will be the effect on the required gain? After inserting the compensator, we find that gain K is virtually the same for uncompensated and compensated system, since the lengths of vector drawn from the lag compensator are approximately equal and all other vectors have not changed. So now what improvement can we expect in the steady state error? Since we established that the gain K is about the same for the uncompensated and compensated system, we obtain the ratio the shown in here. So this equation shows that improvement in the compensated system's static error constant over the uncompensated system is equal to the ratio of magnitude of compensator 0 to the compensator pole. In conclusion, although the ideal compensator drives the steady state error to 0, a lag compensator with a pole that is not at the origin will improve the static error constant by a factor equal to 0 of compensator divided by pole of compensator. So this is our today's discussion on how to improve the steady state error using the compensator. Thank you.